All right, let's go. Do you want to tell me when, or do I just start? All right, I'm ready. Should I just start? For the next about an hour, we're going to be looking at an introduction to axiomatic design. I've got 48 slides that I would like to share with you, and there's a couple places where you can stop and try some exercises. And in a moment, I'll figure out how to make this thing go. There we go. All right. So what we want to do is understand the basics of axiomatic design and apply Sue's axioms. And how to apply Sue's axioms. We want to look at the structure of design solutions, in particular, the decomposition of design problems. And there'll be two other lectures on this, 2 or 3 other lectures on this to follow up on axiomatic design. So axiomatic design is a design method that can be applied to the entire design process for products and processes, as well as for planning. The application of the 2 design axioms assures that the best design solution assures that you'll get the best design solution for a set of functions. Axiomatic design has been shown to reduce cost and reduce design times, and minimizes complexity, maximizes the robustness of design, and we'll be seeing how this goes. So, all right. So the essential elements are the appropriate decomposition of the design and the application of the axioms. And one of the advantages of axiomatic design, as this next bullet points out, is that we're able to look at the best design solutions in the conceptual stage. So we're able to sort out design solutions before we have a large investment, say, in a prototype or even in production. Or before we have a large investment in say, doing computer-aided design. And it applies just as well to the conceptual stage as to the design details. There's 3 books that I recommend that apply to this that have been written by Nam Su, and they're shown here. The first one, The Principles of Design, from 1990, lays out the work that Sue had been doing for about the previous 20 years on developing this special design method. The next one, as it says, is Advances in Applications, and the third one, the most recent one, shows how this applies to complexity. So why would you want to use axiomatic design? Well, lots of times people say better, faster, and cheaper, choose any 2. Axiomatic design has been shown to do all 3. Gets you not only a better design, but arguably the best possible design for a set of design criteria. Do it faster than any design method I know about, and do it at a lower expense. How does it do that? Well, one of the ways it does that is by removing non-productive iterations and reducing complexity. Essentially what this is doing is, you could call it lean design. Axiomatic design also provides metrics for design process and design quality, and I don't know how else you can get those. It helps communicate the design intent, and as I mentioned, select the best design options. So the design problem I would like to be thinking about is sort of theme running through this, is process design for shaft surfaces for rotating lip seals. This may not be something that has crossed your mind as an important design problem before. What is a rotating lip seal? Well, a rotating lip seal is to keep fluids on one side of a rotating shaft from leaking out onto the other side. And so here's a little diagram of that. So here's the fluid here on this side. Let's see, let's do a nice blue fluid. There's the fluid, you can see there. Here is the lip seal, which goes all around the shaft. And the important part, which I'll do in red here, is this zone that is rubbing on the lip seal. The lip seal, historically, there were things like leather. Now they're polyurethane kinds of things. Here's another part of the, it's rubbing on the shaft. So we have this polyurethane material rubbing on, it's very often a steel shaft. And so the question is, how should that steel shaft be textured, or what sort of roughness do I want to in that situation? Well, here's a diagram of showing sort of cross-section of this. And so the key thing is, well, it's being covered up by the arrow, the shaft surface. So what should the shaft surface look like in order to maximize the life of the element that's shown here? So the primary lip is the one that's holding, in this case, the oil back from going outside. And one of the things they're showing here is that there's a little interface so that the somehow the primary lip is being supported by the fluid that it's trying to retain as well. All right, so what I would suggest is that at this point you might stop the video and Google or use your browser to see what they have about radial lip seals and try to appreciate what customers might need or what the customer's needs might be. One of the things I want you to note is that a lot of power is converted from chemical to mechanical and then transmitted out of oil-rich environments by a rotating shaft. And the lip seal keeps the oil where it should be. So every car has this. And without the lip seals, the oil is just going to leak out, and so then you're either replacing oil, you're introducing oil into the environment, and so all these are undesirable. So you need, so there's an important sort of societal need as we look at how we're generating power. So what I would like you to do as an exercise at this point is start noting what customer needs might be for the shaft surface. So, so let's take a look at what customer needs are. And so the customer needs, so what we'd like to say is, well, who are the customers for rotating lip seals? So you might make a list then of the potential customers for rotating lip seals. And then think about what adds value to those customers. So what would each customer value? And then I want you to ask this question: did you think of everything? So is the list collectively exhaustive? So that means, did you think of everything? And we're going to use the abbreviation for this, CE. We'll be coming back to this collectively exhaustive question in other contexts. And so here's an important question to be considering. How can you tell if your list is collectively exhaustive? So if you didn't already stop your video, this would be a good time to stop it. Take a look at what comes up from your search engine under rotating lip seals or radial lip seals. Glance at some of that stuff. You're going to see some sort of definitions, some drawings, some people that are manufacturing them. Then think about the environment in which these are being made. So who is going to be concerned about rotating lip seals? Maybe knowingly and unknowingly. If you buy a new car And after you use it for a little while, you come out and there's oil sitting underneath it when you back out of the driveway. And that oil is leaking out from a rotating lip seal. So that's one of the customer needs, for example, would be not to have oil on your driveway, not to increase oil consumption, or to run mechanical part out of oil. A couple interesting things on customer needs. These are important because they're going to be used to guide engineering functional requirements, and we'll be coming back to these things that we're going to call FRs in a moment. And one of the things to consider is that the customer doesn't always know what they need. TV. I wasn't around, but I bet back before TV was invented, nobody said, I would like an entertainment system that would bring questionable programming in front of my children, keep my kids from reading, keep them inside on sunny days, but that's what a lot of people wanted, and even though they didn't know it. Cars. I'd like a transportation system that's going to make us dependent on foreign oil sources, pollute the air, and kill 10,000 people a year. But that's what we have with cars. Steve Jobs is credited with developing products which people didn't know they needed, and then discovered that, wow, these are great products and I really do need them. Anyway, so the point is the customer may not always know what they need, and some of these products that may not seem in certain contexts to be great products turn out to be. So, and there's always naysayers. But so customer needs. All right. Let's get back at this point then. If you've made a list of customer needs, that's going to get us started on this design problem. And we'll be using that list, so save that. So axiomatic design. What makes this special are the axioms. And so we're going to cover the axioms and then the basic elements to using those axioms to solve design problems. So the two axioms are maximize the independence of the functional elements. This makes the design controllable. It avoids unintended consequences, makes it adjustable. And the second one, so that's the first axiom. The second axiom is minimize the information content. That makes the design robust and maximizes the chance of success. Let's think about design in the engineering context for a moment. So, and when we teach design, are we teaching it in general like an art or like a science? All right. So what is a scientific discipline? How can we teach something like a science? So if a discipline has a few simple, self-consistent laws that can be applied to solve a wide variety of problems, we call it a scientific discipline. So a great example of this is Isaac Newton, who made mechanics much more compact, easier to understand and easier to teach, because he was able to find a self-consistent set of simple rules which governed a wide range of mechanics problems, from describing the motion of the planets to motion on Earth, like an apple falling. So a scientific discipline has this simple underlying structure. But what is an art? Well, art is much more cultural, subjective, experiential, and emotional. So art is going to be much more difficult to teach. So it would be nice if we could teach design like a science. So if we could teach a design like a science, then we would say, well, we ought to be able to somehow tell a good design from a bad design with some simple set of rules. So think for a moment, and maybe pause the video, and write down a couple of ways that you can tell a good design from a bad design. How would you do that? So everybody has had some experience with design and maybe had some experience with good designs as well as bad ones. What are their distinguishing elements? One of the problems when you go to evaluate designs, particularly with design teams, is that everybody likes the design that they created and would like to see their design represented in the final product. So they tend to promote their designs. So designs are like babies. They look good to the people who made them. What we have with the axioms, though, is an objective criteria for evaluating designs. And that's important because it can help avoid prolonged discussions, often that are non-productive, as people are defending their design concepts. So the design axioms are the rules of the game. Axiomatic design, as Mike Schapulski, one of my former students, said, takes you from argument to analysis in design evaluation. And that's important because argument usually brings you through a lot of non-productive iterations, and analysis helps you converge on the best solution in a short amount of time. For design problems, axiomatic design is kind of like a grammar. So practicing engineers have the vocabulary, they know what the content is, they can do the writing, but the axiomatic design brings structure and logic into that process. So you really need both. But if you have the structure and the logic, you can move forward much faster. So where did axiomatic design come from? Many practicing engineers haven't heard of it. It was developed at MIT by Professor Su. He was the chairman of the mechanical engineering department at MIT. He was also engineering director at the National Science Foundation. And currently, he's the president of the Korean Advanced Institute for Science and Technology. If you don't know anything about it, I encourage you to go to the web and see what's going on there. There's some very exciting things. And he's got some interesting projects going, like cars that run off power that they get from the road and through the road or through systems in the road, and mobile harbors that keep you from having to build deep water harbors but can still load and unload ships, which is important for Korea. These axioms were discovered in the late 70s at MIT. And the premise that he started off with is a strange one for many practicing engineers, that somehow engineering design could be based on a self-consistent set of axioms. Actually, good engineering design could be. And that these would lead to the best design solution for all design problems. So if it weren't for axiomatic design, what would the state of the art, or how could we summarize the state of the art in engineering design? And essentially, the other approach is an algorithmic approach. And what that assumes is that if I have the correct process, I get a good result. Well, there's some merit to that. And the correct process will certainly help lead to a good result, but just going through the correct process can't guarantee a good result. And the processes that are often suggested are trial and error, where you need to develop the design often to a prototype stage, test it and evaluate it, and then go back and make some corrections and try another prototype. And those are examples of non-productive iterations. So if we could, early in the design process, earlier than making prototypes, identify the best design solutions, we could save time. One of the things, too, in the state of the art is that evaluation is done by experience. All right, we have somebody that has done this before, knows what's going to work, and can evaluate the designs on that basis. So we build up experience slowly, sort of bit by bit, and then, of course, try to keep that. One of the disadvantages of experience is that it often leaves when the engineers retire. It's hard to pass it on. The axiomatic approach provides axioms and a structure and process for applying the axioms. So we never really escape from the process, but we have a process that is governed and consistent with the axioms. Application of the axioms requires a certain structure, just like application of Newton's laws requires that we have some special sort of decomposition of the forces, for example. Creating the structure requires a process. So we can say there are three essential parts to axiomatic design. The axioms, which are the independence and information axioms. Structure, and that we'll be talking about. There's lateral and vertical decompositions, and a process for creating these decompositions is the zigzagging decomposition, during which we test for the axioms and compliance with the axioms, and then finally integration. All right, so here they are laid out. The axiom, structure, processes. So that's the decomposition of axiomatic design, or at least the way I like to do it for teaching. Axioms, maximize independence, minimize information. Structure, horizontal and vertical decompositions, and then zigzagging decomposition and physical integration are the two parts of the process. All right, let's move along. We've introduced the axioms, and we'll be talking in much more detail about those as we go forward. Let's take a look at the domains, and I want to take a look at the naturalness of the domains. So what are these shafts? Right, the shafts are sitting in a kind of machine here, but we see that there are some shafts. And so the question is, what are these, or how many ways can you describe them? So pause the video again and say, all right, how could I describe these? Are they a particular kind? What are the different ways you could do that? And make some notes. Now, if we do this in a class together, we'll get a greater range of descriptions, and I will describe what some of these will be in case you don't get them all. But let's take a closer look, because what we're trying to do is create a process for the surface of the shaft that is going to interface well with the lip seal, and that means taking a detailed look at the roughness and how to create the roughness. So here in this image now we can see a rendering of a measurement of the roughness of a surface. So what I'm looking for is the domains in the horizontal decomposition. So customer needs. All right, we talked about this, what adds value. Well, you could describe those shafts as something that fulfills a customer need. Make your engine work. You could describe their function. Well, they're to open and close valves. They're a camshaft. So this is what it does. Physical description. What does it look like? So it's a shaft. So that's part of a physical description. It's a shaft with lobes on it. It's a shaft with lobes that aren't concentric with the axis of the shaft. So this means that they can provide a special movement as they're sliding over, for example, a valve stem or a lifter for the valve. And so that's what it looks like, or you could say that it is a ground piece of steel. In other words, you're describing the process for making it. So this exercise where you've written down how you might describe the shaft, see if you can take the elements that you wrote down, or the descriptions you wrote down, and see which of these horizontal domains it fits into, or they fit into. And then let's just reflect for a moment. So as I introduced these, I introduced essentially 4 different ways that we might describe the shaft. All of these are what we would accept as valid descriptions of the shaft, but they are all looking at the shaft in a different way. How does it fulfill a customer need? How does it fulfill a functional requirement? What does it look like? Functional requirement, what it does, what it looks like, or how we make it. And we're willing to accept, I think most people are willing to accept that those are 4 valid ways of describing that shaft. Now, as we're looking at the domains, there are also constraints, things that need to be avoided. So we talk about it as a steel shaft. We want to, say, avoid wear of that shaft, and we might do that just by avoiding materials that are so soft that they will wear. If we're designing that, we want to avoid expenses, and so we're apt not to make it out of a material like titanium, which is expensive and difficult to process. So there's a naturalness to these domains, and this is going to be our horizontal decomposition. Now, we can work with primarily with just 2 of these domains. So much of what we'll be seeing in the rest of this lecture is refers to the functional and the physical domains. Now, the process domain is important. You might be asking yourself, why would we eliminate the process domain? There's the process variables, and we're talking about process design. And so it depends upon how we define the functional requirements. If we're doing, so we can define the functional requirements as creating certain physical things, in which case we can take the process design and use it with just FRs and DPs. Or we could go concurrently and say, well, let's use the functional requirements from the customer needs, things like prevent oil leak, and then let's take, so then we have the physical requirements as to what the shaft surface needs to look like, what kind of roughness does it have, and then the process variables would be how do we create that kind of roughness on the shaft. And for those of you who are not so familiar with this, let me point out that some kinds of roughness will be much more effective in maintaining the seal than other kinds. And we'll get into more details on that. All right, so the point here is that we can work with the FRs and DPs for the most part between the functional and physical domains for much of our discussion without any loss of generality. So let's take a more detailed look at what FRs are. They define the success in design. There's a special burden on the FRs, or functional requirements, and no design can be better than its FRs. That's what we're saying the design is supposed to do. Here's where we're going with the design. So these are the functions that this design is supposed to fulfill. So design is about solving problems. And generally this means changing something. So it's important that the FRs will be independently adjustable. So the FRs usually are talking about something that needs to be adjusted or changed. So they have to be adaptable to change or capable of providing change. Let's take a look at the importance of adjustability. Why should this be so important? Because the independence of the FRs is what guarantees the adjustability in a design. Why should this be the first thing that we need to be thinking about? Well, adjustability accommodates change. Change is everywhere. So the one thing that's constant is change. In case you hadn't noticed, the universe is not in equilibrium. So things are moving, energy is moving, things are always changing. Weather changes, people change. The universe is largely unpredictable. Now, we could, sometimes it's interesting to see how much we have invested in a room full of engineering students in calculus. Why is calculus so important? Why do we stress calculus? Now, we're not always good at explaining that, but calculus models change. So we just said change is important, change is everywhere. And calculus was developed by Newton, according to Gleick's book, in order to describe change, how things are changing. So the derivative of something with respect to time describes how something, one thing, whatever it is you want to put in the parentheses, changes with respect to another, and if it's time, that's what you're looking at. So Axiom 1 is essentially about adaptability. Now, Axiom 2, as we said, is about robustness. And that robustness is really with respect to change. What do you need robustness for? Well, if nothing changes, you aren't even going to notice if something is robust because it just sits there. So the concept of change, which Newton builds calculus around, essentially, is still with us as an important feature, and it comes up in axiomatic design. All right, let's take a look at something and the importance of change in naval warfare. And let's go back now to just before WPI was created, during the time of the Civil War, 1862, just a few years before Washburn shops and Boynton Hall were built. So we're looking at the American Civil War. Now, a couple things, we want to interpret this in the context of axiomatic design. Now, this is well before Nam Su started talking about axiomatic design, so clearly the engineers who were working on these problems didn't call what they were doing by these names, but I believe that good engineers for a long time have understood these concepts intuitively. Why is steam power such a great thing? Well, steam power sort of decoupled locomotion from wind. So steam is going to be a great advantage in a naval battle because I'm going to be able to maneuver my ships in ways that I could not do it if I had to rely on the wind. And if we look at some of the drawings, as we will in a moment, of the naval ships, they were using both. Now, but the battle I want to talk about is between the Virginia and the Monitor. Many times it's called between the Monitor and the Merrimack. The Merrimack, named after a river in New Hampshire, was the boat the Southerners were using. That had actually sunk, and it was raised and rechristened the Virginia. So the special thing, though, that we want to be looking at is one more level of decoupling. And the Monitor, the Union ship, had a swivel turret, and that turret decouples the direction of travel from the direction of fire. So the swivel turret comes up with a new FR, which is adjust the direction of fire. And so this is, let's take a look at how we can interpret this in the context of Axiom 1, maximize the independence of the functional elements. So, so here's a drawing, and again, if you want to pause for a moment and go read about the battle between the Monitor and the Merrimack, or the Monitor and the Virginia, and use your search engine to find that, I think you'll find some interesting things there. So, so this ship is the Southern ship. This is the Virginia. And this smaller one here is the Monitor. We can see the Monitor hasn't bothered. Oh, yes, it has. It's got a little flag up there. It's hard to tell what the flag is, but in any event, oh no, there's that flag is clearly the northern flag. It's hard to tell that this one. Anyway, I digress. Here's something interesting. Notice that the Monitor is smaller than the Merrimack. The Monitor appears to have one gun. I think it actually has two, but we can't see the other gun. The Merrimack has got two, I think, off the bow and the stern, and I don't know which way this goes. And then I think four along each side. So the Virginia, rather. So the Virginia can outgun the Monitor by quite a bit. It outweighs the Monitor by quite a bit, and it is also faster than the Monitor. So traditionally, the Monitor should have avoided a confrontation with the Virginia. But what happened? There was a sort of race to get these built and introduced. The Monitor was being made in New York. Its sea trials were its trip down to Hampton Roads from New York City, but it had the swivel turret. And a day before the Monitor gets there, the Merrimack is going out, and basically it's sinking Union ships at will, because it's low, it's ironclad, and it can go around, and it's fast and heavily gunned. So it's sinking Union ships. Then the Monitor comes down and engages it. Now here is the swivel turret. And, whoops, I got the wrong thing on here. Here is the swivel turret. So this is able to, as this arrow indicates, move independently the direction of the ship. All of the Merrimack, all of the Virginia's guns are fixed. So I want to change the direction I'm shooting, I've got to change the direction of the ship. And right here, at about 45 degrees off, I don't know if this is the port bow or the stern or whatever, but at 45 degrees off the bow and the stern, there is the Monitor can't, or the Virginia rather, cannot fire at a ship. So the Monitor has wisely positioned itself in this area where the Virginia can't fire. This so frustrated the captain of the Virginia that he accused the captain of the Monitor of not being a gentleman. So he did not, a gentleman would have positioned his ship where it could have been sunk. Anyway, so let's take a look at this in terms of axiomatic design. So what we have here is a matrix, and on the vertical axis we've got the two FRs. Adjust the direction of travel and adjust the direction of fire. And here's the Virginia solution. 1 dp, and that's the rudder. The rudder influences both the direction of travel and the direction of fire. That's why we have an X in both of those positions. So that's the design matrix. And so we call this coupled. Now, the monitor has the same two FRs, but it has an extra DP now. And that extra DP is the turret that can swivel. So I can use the rudder to adjust the direction of travel, so that's an X. And I can use the turret to adjust the direction of fire, so that's an X. Now, as I look at this, clearly the turret does not influence the direction of travel, so that's an O. All right, so take a moment and think about this matrix critically and say, what should this element be? We put an X where we have a DP, so we're going down this way and looking to see, does the rudder influence the direction of travel? Yes. Does the rudder influence the direction of fire? Is that correct? Yes, let me digress for a moment. So one important thing is that each FR requires a DP. The FRs cannot be independent unless they each have their own DP. So the Virginia solution with one DP clearly lacks independence, and it's coupled. All right, so now let's get back to this. Is there an interaction here or not? Is this correct? And no, it isn't, because if we think, does the rudder influence the direction of fire? Yes, it does, so this should be an X. When I turn the boat, the turret turns with it, unless I've got some fancy computer-controlled turret, which obviously they didn't have in 1862. So, but we could have now. So as I change the direction of travel, I'm changing the direction of fire as well as the direction of travel with the rudder. So what this tells me is that I have got, in these situations where I have what's called a triangular matrix, as opposed to what I had before. This is a diagonal matrix where I've got, so diagonal means I've got X's on the diagonal and I've got O's off the diagonal. And a triangular matrix is where I have got X's in the lower or in the upper triangle. This is a lower triangular matrix. What this indicates then is that first I'm going to adjust the direction of travel. That's going to do something undesirable to the direction of fire, perhaps. And so then, after I get the direction of travel where I want it, I will swivel the turret so I can adjust the direction of fire. All right, innovation. How do we innovate? Well, change is important. Where can change increase value? What can I do to change something? What new functions could I put in that would increase the value of what I'm working on? So if I come in to a company or I look at a situation and I go, well, that's fine the way it is. I'm an engineer. I'm here to design things. That means coming up with new stuff. But I don't see anything I can change. Well, it's going to be difficult to increase the value. As I make these changes, I want to be able to maximize the independence. So Ericsson, who developed the monitor and the swivel turret, recognized that the change could increase the value. And then, so then the idea is let's maximize the independence of being able to direct fire. All right, so let's take a look at another example. This is water faucets. And the question is this a good design? So what do we have in this design? We've got a cold water valve, and we've got a hot water valve. Is that a good water faucet design? Well, how do you decide if it's a good design? Well, first we need to know what the customer wants. So is this satisfying a customer need? So we really can't tell if it's a good design unless we know the customer needs and generate from those FRs. So when we look at a design and are trying to tell is this a good design or not, we need to speculate on what the FRs might be. All right, so let's suppose that the two FRs are the customer need is to wash your hands, and that means I would like water at a certain temperature, and I would like it delivered at a certain rate. So, so what happens now? I've got a cold water valve and a hot water valve. This is supposed to be up here somehow. All right, so in this design, with the cold water valve and the hot water valve, what happens? Let's take a look at the matrix. Well, if I adjust the cold water valve, that changes the temperature and the flow rate. And when I adjust the hot water valve going down here, that changes the temperature and the flow rate. So this is a fully coupled design. So I don't have good independence, and every time I go to, say, change one of these things, I'm apt to get unintended consequences. So what happens when you go to use this kind of thing? You walk into, say, a washroom where you're not familiar with the controls and what the gains are on the valves, and so you make a guess. You can sort of estimate the flow rate. It's hard to look at it and estimate the temperature. And so then you stick your hands underneath and ooh, it's a little hot. So you increase the cold, and then all of a sudden now the water's splashing out, ew, the flow rate's too high. And then you're iterating. And these are essentially non-productive iterations that are not getting your hands washed. The consequences are not too severe. At worst, you splash some water on yourself, and if you're quick enough, you won't scald yourself. But the point is, iteration is required to reach the desired solution. So often in certain kinds of engineering environments or industrial environments, these iterations can cost money. They can use up raw materials or take time. So the DPs are not addressing the FRs individually. So this fails Axiom 1. All right. So we just stopped flying the space shuttle this year, and that was one of the engineering feats, certainly, most important engineering feats of the last 100 years. And it had, as everybody realizes, some problems. Could we have made a better design using the axioms? Well, what are the functional requirements? Now, again, we can speculate on those. And carry people into orbit and carry cargo into orbit. I think those are reasonable guesses at what the two highest level functions of the space shuttle are for. All right, so how could they be satisfied independently? So one approach, if we want to maximize the independence of these two functional elements, would be to have two separate launch vehicles. Docking problems were solved during the Apollo missions. So we learned that we could dock in space. So there's no good reason why we couldn't have sent the cargo up in one launch vehicle and the people up in another one, and avoided the coupling of having to put people and cargo in one aircraft. All right, let's leave Axiom 1 for a moment, and we'll be getting back to that. And let's take a look at Axiom 2. So suppose we've got a nice diagonal matrix. So the independence axiom is well satisfied, or we've got two designs where we've got an equal amount of independence. The one that possesses the least information, then, would be the best. So what is information in this context? Well, information relates mathematically to the probability of success. And what is success? Well, it is the ability to achieve the FR. The FR defines what we want the design to do. That defines success. So, so Axiom 1 is offering a particular approach to maximizing success, because if we have coupling, it's going to be hard to adjust things so that we're satisfying the FRs. Axiom 2 really is taking it on full. All right, let's take a look at basically everything else that could impact the probability of success. So what we're about really in this is reducing uncertainty in design. And so single FR designs where we just have one FR, and if that's completely satisfied, it's only one FR, then the design is really all about Axiom 2. Let's take a look at one application of this. All right, so the example here is a kind of clamp. And what we're trying to do is to keep these two elements from sliding versus each other. So, and we're going to do this with this clamp. And so this element is acting like a kind of linear spring. And when I move this cam, I go from a minor to a major axis and either loosen the clamp or decrease the clamping force or increase it. And so if I move the clamp into the closed position, I create some force in the spring, and the force pushes these things together. So, so it makes it difficult for them to slide, and I have, and that's what I'm trying to do. So let's take a look at these two things. Here's the question. Would you like for this spring, would you like it to be very stiff or very soft, if you have a choice? So the dP is x, and the FR is this force. There's a certain tolerance we can put on the force, plus or minus F, for it to do the job it needs to do to clamp. And so we can describe the design problem now by an equation, F equals Kx, where K is the spring constant. So let's take a look at this graphically. So we can put the FR on the vertical axis and the dP on the horizontal axis. And then we can take a look at the relationship between them, which is characterized by K1 and K2. So, so the stiff spring is K1, steeper slope here. That's what the K talks about. So here is what we have for our functional tolerance. So let's see how this maps onto tolerances for the dP in the physical space. So if we go over here and then down there and over here and then down there, we can map the functional tolerance onto a physical tolerance. So here's the physical tolerance, because there's where it's intersecting. I'm sorry, that's not what I wanted to do. There's the physical tolerance, functional tolerance mapped onto the physical tolerance. So now let's do it for the other solution. So here we have the exact same functional tolerance, and now mapping it down onto the physical tolerance using instead K2. So K2 comes down, and we see we've got a much larger tolerance in the physical domain. And why is that good? Well, a larger tolerance in the physical domain means that it's going to be less sensitive to wear, temperature, manufacturing variation. So so as things change, the performance will be maintained. It's a more robust design. And we'll get back to this in later lectures, but what this means then is there's less information or lower information content. So often we can take a look at stiffness, or we can use stiffness as a kind of metaphor in other design problems to get the best possible, largest possible physical range or physical tolerance for success. All right, so there's many things that we can do in improving yield, comparing delivery options even, and they're all tied to the probability of success. Let's take a look at a design example that has got, seems to have nothing to do with engineering, and I want to try to establish how broad the application of these axioms are. So this might seem like a kind of funny example, but it's got some opportunities to learn. So let's take something that seems to have nothing to do with engineering. Let's design a vacation. So what are the two things we might want in a vacation? Well, it's, I think, being able to relax and maybe romance, if we're talking about by somebody. Well, anyway, let's just suppose that's what you wanted, whoever we're talking about. All right, so the initial proposal for this would be, all right, well, let's maybe have some nice cocktails or wine or beer for a little relaxation, and for the dancing, or for the romance, let's see if we can supply that by dancing. What does our matrix look like? Well, if we think about what the ethanol might influence, we chose it to relax. But it also has the potential to impact the romance. If we have too much to drink, we may become somewhat unattractive. Now, the dancing, if you dance as badly as I do, this will not provide any relaxation, so it's not going to have any impact on the relaxation. And it was intended to satisfy or fulfill the FR for romance. Now, in fact, the situation could even be worse. So what this is implying, again, we've got what we referred to before as, remember, a triangular matrix. And so what this implies first is that I need to take the ethanol I need so that I'm relaxed, and then this could have a negative impact on the romance, and then I got to correct that with dancing. Well, it doesn't take much experience to realize that the ethanol can overwhelm the situation, and that no amount of dancing will be able to fix the ethanol problems. And so in this case, we ought to be looking for an alternative that will not impact the romance, and so that we could have instead a diagonal matrix, which would be better. So what about if we look at yoga as an alternative? And then, indeed, we could say the yoga is going to won't have a negative impact on the romance, and so we have what is preferable here is a diagonal matrix as opposed to the triangular matrix. So, not surprisingly, ethanol is not a good design solution because it influences too many things, and so has unintended consequences, and yoga is a more independent solution. And think, flexibility, adaptability. All right. Two axioms. Maximize the probability of success in satisfying the design functions. A couple design, which violates axiom 1, has less chance of being successful because it's difficult or impossible to adjust. So after you remove the coupling, satisfying axiom 1. Then you apply the axiom 2 to maximize the probability of success. So, so again here, let's, as we conclude this first part on axiomatic design, think of some examples of products or systems, in particular processes, that suffer from unwanted coupling. So systems could be a process as well. And what are examples of products, systems, processes that have too much information? So what we're looking for are what can we see some examples of things that could be improved by the application of the axioms. Now here's something. As you're looking for these, think about what's frustrating. What are the things that I'm not looking forward to having to do? Why am I not looking forward to having to do those? Are there some things that are linked? And think about the way things are changing, or my inability to make adjustments. All right, important things. The most important thing, there's a lot of low-hanging fruit in engineering and engineering design, that can be addressed by independence. So avoid unwanted coupling. So that would be the one most important takeaway. All right, so here's another chance or another place where you could stop the video, take a look at these questions, and try to answer them. After you've done that, then you can advance, because the next slide is going to answer these questions. And so there are the answers. And now for homework, download Aclaro. There should be some instructions on the MyWPI site. Figure out how to enter customer needs. And Aclaro is fairly intuitive, and there's a help file there. And then this is going to be in preparation to entering and decomposing functional requirements and design parameters and process variables, which we will get to in the next lectures. Thank you very much for your attention. Now, if everybody hasn't already gone home,